Okay, welcome back to session 5, our last session of the day. If your brains can cope with it, it's been a very in-depth discussion today. So we are going to be looking at what are the MIP needs now, and Stephanie Fiedler is going to chair this session, so I'll hand over to her.
All right, thank you so much for the introduction and welcome back to the workshop. The title of the session is What are the MIP needs? And we're really having a lineup of very interesting talks. The first one is going to be presented by Jane on the population density data. We follow with the presentation by Maria talking about hydrogen. I will present on behalf of a larger team of what we know about dust emissions. And then at the end, we're having Dave, who's talking about land-only and ocean-only atmospheric forcing data sets. And the idea of the session really is to see what are the needs for other contributed data sets from the forcing task team. So are there scenarios or idealized data sets that you would need for making your MIP happen? And ideally, we would like to have towards the end of this session a list for the points of context for forcing data delivery, whatever you might need. If you would like to contribute to this, feel free to join the discussion verbally at the end of each talk and towards the end. And do feel free to list your needs also in the Padlet. So there's a very nice column at the far right where you have to scroll over and you can list there what is needed, and we have a very concise list towards the end. With that, I would like to hand over to our first speaker, who is Jane Mulcahy, on the population density data, highlighting the need from the model's perspective.
Thanks, Stephanie. I'll just see if I can share. Okay. I think it's coming. I just pressed the wrong button, sorry. I'll just put that into full mode. Not gone to presenter mode. Hang on, let me try that again. Sorry about this. We'll try again. Doesn't seem to want to go into presenter mode.
So we came back out.
So you have to share your full screen.
Okay.
I have to share my full screen, but it means you've got no notes.
Okay, that's fine.
It won't let you see your notes.
I can make that up.
Which was dreadful for me.
So screen.
To click on the screen.
Click on the screen. Yeah, and then share.
Okay. Hey, okay. Thank you. So I'm going to talk a little bit about, a new forcing data requirement that's cropped up for our CMIP7 activities around population density, and also I'm going to chat a little bit about the Human Development Index as part of that as well. And so, yeah, if you hadn't had enough of fire before the coffee break, I'm sorry, you've got to endure another couple of minutes, but I'll try and keep it brief. So this is, not surprisingly, given the amount of talks we've had already over the last couple of days around fire, a lot of the Earth system models now are moving in towards the space of having interactive fire modeling and having that interactive fire modeling capability fully coupled within the Earth system. So really being able to simulate those fire atmosphere interactions and the feedbacks onto the vegetation dynamics, and also importantly that climate feedback onto the fire in itself. So we really want to have that fully coupled system. So this is showing kind of a schematic basically of kind of what we're planning with UKSM, where we're implementing the Inferno fire model. And essentially here we need to estimate fire ignitions and suppression, combine that with flammability to kind of estimate a burnt area per PFT fraction. So the requirement around the population density comes into this kind of ignition space. So here we look at the total ignitions, and again, that's both an anthropogenic component and a natural component. So the natural component comes from lightning, which we have within the model. And so the anthropogenic component comprises of both suppression due to human activity, but also obviously ignition due to human activity. And on the right-hand side here, you can see how the ignitions, the fire ignitions kind of vary as a function of that population density. So there's initial kind of peak as the population density increases, and then decreasing as the increasing population obviously contributes more to the suppression of the fires. So this is where our kind of requirement comes from. And in terms of the data sets that we're currently used, we are using the HIDE data set. So I think for the pre-industrial and historical, this is kind of pretty well provided for currently. I think it's maybe version 3.1 that they've been using in UKSM to date. So we've got the full historical period covered. I think where the problem kind of starts to come is as we move towards the SSPs and the scenarios. So in theory, a lot of this should be either supporting the IAMs or as an output from the IAMs. I'm not an IAM expert. But João Teixeira, who does a lot of the fire modeling, provided this plot here in terms of how the historical data combines with what he found in terms of a future scenario. I think here he's looking at SSP. And you can see that there's a mismatch. So there's kind of a missing kind of harmonized gridded data for the SSPs. So and also access to that data. So that, getting access to this SSP involves kind of emailing groups individually and kind of requesting data and getting that offline. So having that data more readily available as we move towards more ESMs, doing the interactive fire modeling, I think could be really beneficial, and also would ensure that we're all using a consistent population density approach as well. So really there, the key message is kind of really when it comes to the scenarios, kind of having more access to the kind of harmonized data between the historical and all the future scenarios. One thing we're looking at where we'd ideally like to go is actually a step beyond population density and actually trying to incorporate the socioeconomic factors into the ignitions. So this is something that João Teixeira has been working on. And again, the schematic or the plot on the lower left shows how, again, ignitions vary as a function of this human development index. So this is a little bit more complicated. So it's not just population density, but varies as a function of kind of GDP, I think, is incorporated into that index as well. And so again, you can see on the right-hand side, he's got a map of a kind of a present-day plot of the human development index. And obviously, the more developed the country, the higher the index, the higher the suppression. And so that's reflected in the bottom left plot. But here, there's really a lack of consistent data, even for the kind of historical period. The data isn't very well provided for. Some of the data that João was able to get access to, wasn't gridded, and so he had to make his own assumptions about how to incorporate that into the model. And really, there's nothing really there that we could find for the future scenarios. So in truth, probably a lot of this data is there somewhere, but it's not in the format and readily available for input into the fire models, I would say. This is kind of going back to maybe something that Douglas was showing before the break. So this, I thought it would be just nice to show why we want to do this as well. So this shows, now these aren't actually fully coupled simulations. These are atmosphere only simulations, but, moving from the historical into the future and comparing the prescribed emissions in CMIP7, so for all the different scenarios in the colored solid lines, versus what we get when we implement Inferno with this human development index. So you can see here, again, recognizing we haven't got the full coupling capability within this particular experimental design at this point, but you can see that there's key differences and huge differences really in what those future emissions might look like. So this is important, and I think having the ability to model that consistently will be a real positive, I think, for CMIP7. And something really new to come out of CMIP7 as well. So I've just kind of tried to summarize the key requirements here. So I would say priority 1 is to have the population density. So this is the very basic thing that we will need. And then probably priority 2 for us, now this might be a little bit more niche to what we're planning in UKSM and mightn't be as widely applicable across other modelling centres. So it'd be interesting to hear their thoughts on that. But certainly all the fire models would be looking at using population density. So that would be the key priority. I've also put a little bit here on timescales kind of to help with a little bit of prioritisation. So again, this is again only coming from a UKSM perspective. So we would need to incorporate what other modelling centres were planning in the space. But as I kind of alluded to earlier today, we're probably not going to have this interactive fire capability for the fast track, but we will be using it beyond the fast track for the wider community MIPS, and we'll be very much probably rerunning the deck and the scenarios with our UKSM2 model, which will incorporate that capability. So it'll be quite hot on the heels, really, of what we use for the fast track. So we're looking to have something, you know, running really kind of mid 2026. So hopefully that kind of sets the scene in terms of what our requirements are and when we might want them for. And with that, that's it. Thanks, Stephanie.
Thank you, Jane. Questions from the audience in here, online? Yeah.
I was just going to ask the question, which kind of came up in my head actually as Douglas was talking. So consistency across forcing data sets, as we start to expand what we're collecting, HIDE and the land use data set are very consistent, correct, Louise? Okay. So in that case, with what Douglas was talking about, is there a consistency mismatch that we're starting to introduce as we start to think about more and more and more? I don't know if this is something that's worth talking about or not.
So the HIDE land use. So yeah, the HIDE land use data is used in the land use harmonization data set. We also use HIDE population data, so it would be consistent in that sense. I think we're on different versions, but we do use it. We don't provide it as an output, so we're not going to be inconsistent with outputs, and we're not using any future scenario population data at the moment. So yeah.
Yeah, so I agree. We would kind of want whatever we use to be consistent with what, you know, you guys are using. So at least all the CMIP7 forcings are then consistent in that space. So clearly we should upgrade what, you know, the versions we're using if they're provided.
Just a quick question, Jane. Did you use population density data in CMIP6?
No, I don't think so. Yeah, no, we didn't have the interactive fire capability in our CMIP6 model. Potentially offline for ISI MIPS, you know, offline fire modeling. Although I don't know. Yeah, Inferno contributed in there, but I think they used the HIDE data set in that potentially.
We have a question online from Steve, I think. Yeah.
Sure. I guess, I mean, HDI, I mean, we don't generate that, but we generate population. I mean, we have inputs. That sounds almost like a SSP, because SSPs provide population, income, and education levels. So that, can you derive it from that? I mean, that really seems like the fundamental data, and we don't really do anything more on the IAM side. And then on population density for the future, actually, Louise, have you identified a source for that, or are you generating that? I don't know if we've identified a source for that yet.
No, we're not using population density in the future in the land use data.
Okay, so you don't need, yeah, I'm not sure we've identified a source for that. We thought maybe we do, but I haven't heard back from them. So sort of an open question for that. And I also had a comment on the HDI approach, but that's online. We can discuss it there.
Okay, thanks, Steve. We have a question in the room from Matt.
Yeah, just to note that so for CMIP6, or for the original SSPs, let's put it that way, which were then processed as part of CMIP6 and Scenario MIP, there was gridded population that was generated. So that was by Brian Jones and by Brian O'Neill, if I remember the paper correctly. Yeah, I have no idea with what consistency that was intended to be, or with what level of fidelity that was intended to be consistent with HIDE or not. But maybe they're worth reaching out to. But I wanted to also bring in that this is now we're talking about a data set which is critically important also for the impact community and for EasyMIP. And so they're also, so what I think it's very important that whatever is used here and decided here is made, that decision is made in conjunction with EasyMIP so that there's consistency also with the downstream impact estimates. And my understanding, and Steve, maybe you were talking about the same thing here, is that there is a desire within the scenario MIP, EasyMIP world to actually do again the gridded population. I think it will be by Brian Jones, but basically I think it's useful for this group to raise their hand and sort of interject that, okay, we want a consistent data set for this because it's also going to be a forcer for the ESMs as well. And we definitely don't want inconsistency between what the ESMs were assuming, the IAMs were assuming, and the impact models were assuming.
Thanks for that comment. More questions? Comments? Okay, then we move on to the, okay, Luis.
Stuck one in at the last minute. I guess it's a question just following up to Matt. So is that population data in the scenarios, like is there a single population data set across all scenarios, or does each scenario have a different data set? And because you mentioned one name producing the data, so it sounded like maybe one data set, or are they producing a population scenario for each different scenario?
So basically there were, in the original SSP timeline, there were actually 2 different population data sets generated, and that was on a per country basis per SSP. So there were different population data for every country and every SSP. In addition to population, as Steve pointed out, there was also educational attainment. There was also urbanization, right? So like all of these sort of drivers were generated. And I think the final version was KC's, right? Yeah, so KC Samir from EASA sort of did all of that data set generation.
So those were like inputs into each of the different IAM models rather than an output of the models.
Yeah, okay. So a model, so if a model says that they are an SSP, they're following all SSP1 assumptions, that would include the assumptions for population per country, et cetera.
Okay, thank you.
Very quick question, Matt. Did Brian process the population data set for historical as well? So historical and SSPs, or was it just one?
So I welcome other comments from the floor, but my best recollection is that it was only for future scenarios. But maybe it started in like 2010, for example. I don't remember when the data set started, but I think it was only for the SSPs.
So it sounds like the data should be there and will be provided for the IAMs to generate the next set of SSPs for CMIP7, but then it's just providing it in a format, because obviously maybe your format is different in terms of you go by country and we go by, we need a gridded data set that then is consistent with whatever's provided for the historical. So there's, again, that harmonization would need to be done.
You want to take it or should I?
I think the answer is yes. Basically, the new population projections, they're ready, and they were also provided or made by Samir Casey from EASA. Then the question is, that is the country level population projections. I don't know who is now doing the urbanization scenarios, and that's the urbanization effort takes the population projections, the country level population projections as an input, as far as I understand it. And that's probably also where the gridded information is then coming, so the density. And so I would also reach out to Brian then to ask, and now is probably a good time, and probably loop in Samir KC then as well, to try to make clear what the requirements are and how to, whether this is going to be consistent or not.
And Steve,
jump in,
no comments.
Yeah, jump in quickly. The previous population projections that Brian and Brian did were based on the gridded population of the world, so it wasn't based on height. So it had a different base data set. So they are different in fine detail, although certainly many similarities on large scale. I also queued up an email. I sent an email to Brian O'Neill and Matt to try to follow up on this.
So it sounds like you're going to follow up on it, Steve, is it?
I'm trying.
Great, thank you. That's what I like to hear.
Fantastic. Did you want to make one more comment, or is it? Okay. Then we move on to the next presentation, which is going to be an online presentation by Maria Sand on hydrogen. Maria, are you there?
Yes. Hi.
Hi.
Good afternoon, everyone. And so I can share my slide. Let's see. So you see this? Okay. Or share?
Not yet. It's coming now. Now it's there.
Good.
Over to you.
Okay. So thank you. So I will present some work that we've been doing on calculating the global warming potential of hydrogen, which has been a concern also the industry because they're concerned about the leakages of hydrogen and how this will affect the climate, and also add some thoughts on the modeling of hydrogen. Well, just an overview of what happens when hydrogen is emitted into the atmosphere. So this is not dependent on the production method, but just hydrogen itself being released into the atmosphere, quickly reacts with OH, and then competes with the same sink as methane. So we have increased methane levels in lifetime. You also have, via various reactions in the atmosphere, you have increased ozone in the troposphere, and also some changes in the ozone layer. We see different, we don't see a big change in the ozone layer, but you do see also increased production of water vapor in the stratosphere. So you have these three main climate impacts on methane, ozone, and stratospheric water vapor. So just to introduce the team, we did then set up with 5 global atmospheric chemistry models, and this also 6th one. We did some budget calculations, and here is the methane ERF per hydrogen flux. To see the different models, we perturbed them with hydrogen surface concentrations, adding 10%, and then also the 2 last models there are with emissions of hydrogen. So you see that the models agree quite well on the methane ERF. We also, this is the ozone total column ERF per hydrogen flux. And then the final here is the stratospheric water vapor. One model did not have the stratosphere. A bit more spread, but still we're quite confident. We also did look at aerosols, but we didn't find in this setup anything of a big change there. So our calculated global warming potential 100 of hydrogen is then, as a model mean, 11.6 and plus minus 2.8. That's one standard deviation. You see here the results for the different models. The model mean is from the 5 first. And this compares good with other estimates of Warwick paper. They used the GFDL model and Hauglandstein, the UKCA model, and Hauglandstein, the GFDL model. And this is double of what was the first work of Dick Durrant. So go a little bit into the atmospheric hydrogen budget. So hydrogen is emitted via various sources, so incomplete combustion sources of fossil fuels and biomass burning, in addition to these leakages. And then you have a big source of the photooxidation in the atmosphere. You also have some debate on if it's on natural sources, but you see the spread here from 0 to 20. And then you have the hydrogen sink, so that's the OH sink that I already mentioned, and then a big soil uptake. And this is what differs hydrogen from methane because of this large soil uptake, and also why hydrogen has a lifetime of approximately 2 years in the atmosphere. So for a future atmospheric hydrogen budget, it will depend on the emissions of other components and, well, available the scenarios as so photooxidation important with the methane and the VOCs, and the future hydrogen will depend on the methane in the atmosphere, and also the fossil fuel combustion and possibly increased leakages, and then also the OH sink with the CO and NOx. So what data are available? There's no current hydrogen emission files, but what we have used and what Fabien Palot has published is based on CO, because they have a lot of the same sources. So here you see the total emissions in teragram hydrogen per year from pre-industrial times, and then split into the anthropogenic and biomass burning and so on, as you can see, and then a fixed nitrogen fixation around 6 teragram. There's no estimates of hydrogen leakages in the SSPs, but there are some that have hydrogen energy as an output. And then you can use this, well, you can use this energy to convert it to mass, and then assume some hydrogen leakages for the future. So one way to do this. And how large are the leakages? So this study is an overview of what we know so far. There's not much direct measurements of leakages. So this is based on assumptions and different calculations and model simulations. And well, it shows that we have no clue. But the industry is starting to measure more and more leakages as they are aware of this climate impact. Also, it doesn't make sense to lose this costly hydrogen. So I assume we will get a better knowledge on this soon. So some thoughts on the modeling, just at the end here. So for present day to pre-industrial, it might be too small of a forcing perturbation for hydrogen for the fixed SST runs. So what we did was the CTM mode, or highly nudged, with a 10% increase in the hydrogen surface concentration or emissions. But you also need to take the methane-induced impact into account. So how the changes in methane changes the ozone and stratospheric water vapor and methane itself. We did that with additional runs. And as I said, there's no emission files for hydrogen at the moment. So what we use is the CO proxy. But we have started now Highway, which is a New Horizon project where we're going to look more into this. So we will create emission inventories and scenarios for a future hydrogen economy. And this is IASA is a partner of this project, but it will not be available for, well, I think 1.5 years. So a bit late, but yeah, you can check out. We just started if you want, and the paper that showed with the global warming potential is published. So yeah, thank you.
Thank you, Maria. Questions in the room or online? Yes, please. Okay. Do you want to go first?
Super interesting study. I had 2 questions, which one is, how many ESMs do you think are set up to run with hydrogen now? Like, if we did have hydrogen input files, would people say great, or would it kind of, they sit in the cupboard for a while? And then 2, how did you deal with the really short lifetime of hydroxyl? Like, do you end up trying to model it directly, or do you parameterize it, or do you have some other clever way of dealing with it? I'd be very interested to hear how you deal with the hydroxyl question.
Okay, yes, thank you. So I missed your first question. So we ran with a full chemistry, and well, we can't measure this, but we assume that it's and the models agreed on the sign of the change of the negative change in the troposphere and the positive change in the stratosphere. And your first question, sorry, if you can repeat that.
if we had hydrogen emissions already, how many ESMs do you think could actually use them?
Yeah, so that's a good question, and because the forcing is so small, so so I'm not sure. I guess you would need at least a forcing of 0.2, but yes, I'm not sure how to set up this, because we set up with the chemistry transport models, and also GFDL was nudged to WINS, but it was so Fabian had troubles with the noise in those models, but figured out a way to nudge it in the correct way. So I'm not sure how. We would also need a big spin up for the stratosphere. But yeah, I think some nudging is have to be in place.
Okay, thanks. Steve?
Yeah,
Did you-
very nice work. Actually, I don't have any comments on the work. I enjoyed reading the paper. Just to comment on the emissions, the big issue with some people know this already, but the big issue with hydrogen leakage is that up until this year, there have been no instruments available to measure it. So you can buy an instrument to measure hydrogen at the level of making sure your building's not going to explode for regulatory purposes, but there has been no instrument available to actually measure leakage at this fine level. Now, when EDF asked an instrument maker about this, said, "Oh, we can do that, just nobody asked us." So they asked them. So to my knowledge, there are two instruments in the world that can measure hydrogen leakage. One of them's in Europe, sitting in Europe now. One of them's in the US. They're testing them out. They are very finicky. They are very much research instruments, but hopefully we will get some of the first ever measurements of hydrogen leakage soon. The hydrogen as a result of combustion, there's some basic chemistry that constrains that. So to the extent we know CO emissions, which is not as good as we'd like, but to the extent we know CO, we have some ratios that are reasonable. The emissions from hydrogen facilities are the part we have no clue about, literally. And that's really going to be a focus of measurement campaigns over the next couple of years, is to figure out how much hydrogen is actually leaking when you're actually using hydrogen on site or transporting it and doing these things with hydrogen. And then at that point, we'll have a better clue on hydrogen. So we're developing inventories, but they're incredibly speculative at present until we get some of that data. But of course, the other piece of this is that what Maria showed is that we don't understand the hydrogen biology in the soil well enough either. So there's this huge uncertainty in the lifetime because we don't have a good handle on the soil sink.
Yes, and thanks, Steve. Yeah, I agree, and the soil sink is the biggest uncertainty here, and we have worked. So this is a project we actually had the final conference today on hydrogen, and we had user partners there, and Shell and Equinor are starting to have instruments, and they have Equinor has now had some measurement campaigns at their sites in Norway, and they are testing their instruments, and a lot initiatives in the US as well. And that's been a lot have happened during these 4 years. It's very interesting to follow, and how quickly the industry adapts. And well, I guess a different funding situation, but a lot of instruments are now being developed. And as you said, they were mostly for safety, so they couldn't really measure these small leakages. Yeah.
And just another comment. And for the IMs, some of the IMs are starting to do hydrogen. It's not going to be in this version because it's not really in the core versions of any of the models. But I think in the future that will come soon. And one of the considerations we do need is that the way you use the hydrogen can make a big difference, right? If you're transporting it or using it over a long distance, then you have much more potential for leakage. The GWP looks scary, it's 20. However, that's GWP per mass. Hydrogen has a much higher energy per unit mass. So per unit energy, that GWP is much smaller. So it's not quite as scary as it looks. But of course, the leakage rate may be higher. It's a very slippery molecule. But in our analysis, for example, we find that basically economically, for the most part, use hydrogen on site, that you don't transport it long distances, except maybe for use in airplanes or ships. So there's a lot of interesting things that are developing in the community over the next couple of years. So stay tuned.
Thanks, Steve. We have a question from Zap.
Maybe back to you, Steve. I'd be interested in your thoughts on also tracking the hydrogen that comes from fossil fuel production. Because if you stop burning fossil fuels, you lose a source of whatever it was, 20% maybe, if I can remember the numbers correctly, which can partially offset any increase from adding a hydrogen industry. So
I think you mean that, yeah, hydrogen, it's not the fossil fuel production, but it's the fossil fuel combustion. It does hydrogen. Right, and that's something the integrated models would, of course, take into account, yeah.
Yeah, I was surprised. We did some back of the envelope with this, and depending on what emissions factors and stuff you assume, in some scenarios, we thought we might actually get less hydrogen in the atmosphere because you stop burning fossil fuels and you don't replace it with something else.
Yeah, it all depends on the leakage rate, which we're guessing at.
All right, thanks for the interesting discussion. Are there more comments or questions on hydrogen? Okay, then we move on to the next topic. Thanks again, Maria, for sharing.
Thank you.
The next topic is desert dust. And I'm sharing my presentation here, which is really about deciphering the role of desert dust aerosols in the next phase of CMIP. And it's really something that I like to think of storms. So it's really quite fantastic when you think of them as long as they're far away. But when you stand in front of it, you can already imagine that it's something that you probably don't want to be in there. Yeah, so it's a air quality hazard. It has multiple implications. And there are several implications of what desert dust is doing. Just try to hide my little thingy here. Now, in terms of the effects of aerosols, desert dust aerosols, is to be specific on the radiative forcing and climate in general, we are really facing quite large uncertainties. And that's something that Jasper was putting together in a review article in 2023. So I borrowed this this figure from him. And it's really quite complex. So let me walk you through this. So the first part is really about direct radiative effects. So we're really thinking about the radiation influence in the short wave and in the long wave. So different from anthropogenic aerosols is really affecting much broader the radiation spectrum. And there are influences on clouds, but we really have a very low understanding of how dust is influencing them. So it's really ranging all the way from warming and to cooling. So we really can say that we don't understand, not very well. We don't really understand how this is working. And there are also other aspects of desert dust. For instance, atmospheric chemistry is really involved in this, where you have either warming or cooling effects, depending in which way it is going. And you do have a fertilizing effect. So you increase even the CO2 uptake from the oceans. So it's really quite broad range, so to speak. When we take this together here in this review article, we think it has a cooling effect, so minus 0.2 in the mean, but you can see from the arrow that is actually really large. So similar to what we know about anthropogenic aerosols or don't know about anthropogenic aerosols, there's a large spread. Now, when we think of desert dust aerosols, they're really having quite large impacts, not only on climate, but they can really be transported far, which means it's not only a problem close to the deserts themselves, but even further away. They are a real risk. So from the image at the beginning, you can already infer it. It's really a weather hazard. It is influencing traffic, both for the air, but also when you think of highways, when you run into a dust storm, it's really quite a problem. And it's influencing how the soil is eroded. So if you have a fertile soil, it can also be deflated and be lost. It does have quite some impact on human health, both in terms of the PM concentrations, but also in terms of how many, let's say, additional contaminants are transported. So if you inhale it, you can be have influences. We did touch on the fertilizing effect. So it's influeing, for instance, the carbon cycle in the ocean. So when you have a dust plume, you often see when after dust storm plankton bloom. So that's something that you see here on the right figure. But it can also have influences on ecosystems on land as far away as the Amazon rainforest, just to illustrate this here in this context. And without going into details, but just by imagining how the aerosols, the desert dust aerosols, are influencing the shortwave radiation transfer, it is quite obvious that it would also have quite some impacts on PV power production, not only because the aerosol is in the air, but they are also deposited onto the panels such that you actually have to clean them. So aerosols from the desert have quite some large influences. And as I said, they're not regionally constrained. So it's not only in the deserts themselves, but it's really something that you can see almost globally. So there are different deserts around the globe. North Africa is the most active desert in this sense, the Middle East, Central Asia too, followed by East Asia. And the deposition is really going in all sorts of directions. So it's not something that is really constrained to just be a local factor. And that is important, or at least we think it's important, but, and that's a very important but, our climate models are not really covering how the aerosol is changing from the deserts over the historical time period. This is something that we have touched on in the previous session already, and Jasper has really been putting this together here quite nicely. So it's the percentage change in global dust mass loading since the more or less pre-industrial, so around 1850, and it has increased by about 40%. And that's a large increase. None of the models here shown in this graphic are really representing that. And he's been thinking about how we can resolve this. And what we have now is a new dust emission inventory. It's called DustCom, which is covering at the moment 1841 to 2000, and it's going to be extended. It comes in 3 different flavors. It has a gridded dust emission inventory, which is most accurate when you want to simulate historical dust changes. But if you use that in the models, we would lose the dependence of the dust emission on climate, specifically the wind-driven emissions. So you would introduce some inconsistency there. There are decadally varying regional or global scaling factors. So both of this is available, and it could also be used in the models to prescribe or better to say, to induce the changes that we've seen in the historical period. It would reproduce the regional and global dust trends. It would preserve the dependence of the dust emission on the environmental conditions. Specifically, if your model is producing high wind speeds, you would simply increase or decrease it in the region, depending on the data set or the local influence in the data set. And the dust spatial distribution, though, is less accurate, because if you have a bias, say, in the spatial distribution of the desert dust aerosols, you would preserve that bias, so it wouldn't be corrected. On top of this, there's already a decadally varying 2D dust optical depth data set coming with this. This is computationally fast, because you would really be able to reduce the amount for emissions concentrations and so on and so forth. You would really read in the dust optical properties right away. And it also enables models who do maybe not have an interactive dust emission scheme at the moment to induce the historical changes. So these are the 3 options. Jasper has put together a manual how one could use these options. So feel free to go there and give feedback. Yeah, so this is really a draft, and we would want to know, is this something that modeling centers can work with? Is this something that you would be interested in to do? Because we have already a blueprint on how one can do this from Aerocom, and we are planning in CMIP to do something similar along those lines. So your input is very, very welcome there. Just to say from his work, from his colleague, we already know that we can reproduce the dust aerosol optical depth changes relative to the pre-industrial. So that's something that is shown here again from the reconstruction from Jasper in black. And CSM has been using the emission from DustCom and is really getting the dust aerosol optical depths correct. Yeah, so it's more or less sitting on top of each other compared to the other models from the historical, which are not capturing this, which is here shown with the dashed lines. So as I said, there's a proof of concept from Aerocom already. 8 models participated in this. So there's quite some interest to actually make this better in the future, especially for CMIP7, hopefully also. So there is already knowledge how to do this. The experiments that I run in AeroCom are experiments with prescribed sea surface conditions. So really sea surface temperature, sea ice, that's all prescribed. So it's not fully interactive. For the climate response, that's sort of limited. And also to point out here in the dust optical depths are these sort of stepwise changes. And that has to do because in AeroCom, they really used 10 years in a row, always the same perturbation. In MIP, we would really have linear interpolation to make it smooth, to look into climate responses and feedbacks. Now, in MIP, we're going to do an experiment for constraining the dust, but of course there are also many other things that we would like to do, and I don't want to go into details here, but just to mention that it's really meant to serve the community for aerosol and chemistry. We are looking into process understanding, feedbacks, air quality, and sustainability, and it's really quite broad. So there's a large request, I'm afraid, again, for the modeling centers for experiments. That's something that we're currently preparing. And we would really like you to participate in this. Now, for the dust emission themselves, what is currently happening is that the data is going to be extended up to 2023 and maybe further, depending on what the historical will really look like. There are 3 different boundary data types for you to choose from. So you could look into this and say, we could do this, we could do that, but really not the third option. That would really help us to develop the protocol. So we would really like to hear back from the modeling centers. And what will be there too is 3 simple future scenarios. And when I say simple, it's really a simple increase, continue as at present day, so keeping it constant, or a decrease. So just for you in the modeling centers to be able to use that also in the scenarios if you want to. Yeah? So if you want to have a consistent prescription from the historical all the way to the scenarios, then this would be possible. And as I said, in MIP, there is going to be at least a historical experiment, maybe also a future experiment with prescribed dust. The boundary data will be available via input from MIP, so we already have been starting this process for getting it in there. Support will be provided, so similar to, for instance, Simple Plumes, we're really there to help implementing this and getting this on the way. And there's also simple dust plume parametrization in preparations, but that's going to take a little longer, maybe 1 or 2 more years, but that's also there at some point. Now, what do we hope to achieve with this? We hope to generate really a new opportunity to fill the gap in our knowledge what the trend in dust, so really these 40% increases in dust really mean for the climate response and the feedback, to really better understand what it means, and also to quantify the role of the missing representation of this dust increase for the forcing and the response. Thank you. Now, I feel a bit strange to invite questions to my own talk, but I do it anyway. Questions, comments? Paul?
Would you like to ask yourself a question?
Seems weird, talking to myself. So you all agree it's important, that's good.
Quick question.
Yeah, Vaishali.
You expect the implementation of this dust data more as a sensitivity rather than a standard historical simulation?
Yes, that's right. Yeah, so there's going to be a standard historical, like in the deck, of course, that we're requesting, and then on top of it, we will see what is the difference when we prescribe the dust. Yeah.
Okay, thank you.
There's a question online from John.
Yes, so when you say that CSM was able to reproduce the dust trends, is that just forcing the global simulation with a globally fixed map of dust tuned to that AOD trend, or is there something more mechanistic about that? What am I supposed to have learned from you being able to reproduce that black line with the red line?
Yeah, so in this experiment, they prescribed the emissions directly and then looked at whether they reproduced the dust aerosol optical depths. So of course, it's not an entirely, let's say, independent comparison, but at least it's the first step to see whether the model is getting it right. But it's not a completely independent assessment. Okay, more questions? Otherwise, we move on to the next topic.
I was just
Jane,
going to
sorry.
say, Stephanie, no, it's okay. It's more a comment really, and I just think actually that it's really interesting. I find it more interesting actually, and I think it's a really nice study you've done. But I find it more interesting that why are the models not capturing the increase in dust emissions over the historical? And actually, the Jasper Cox reconstruction looks like a really nice constraint that we can use to actually understand our Earth system models better as well. So there's probably a few things we can do with that. So thank you. It's
Yeah,
really nice.
absolutely. It's also a validation tool. Thank you. All right, then we move on to the last speaker of the session. That's going to be online by Dave. Can you hear us?
Yes, yeah, I can hear you, yeah.
Okay.
Let's share my screen.
Yes, please. So Dave Lawrence is going to present land-only and ocean-only atmospheric forcing data sets. We're really glad to have you. And as soon as you're ready to share the screen, I hand the word over to you. We can see it very well. Thank you.
Great. Cool, thanks. Yeah, so yeah, thanks for inviting me, and I'll talk to you a little bit about sort of land-only and ocean sea ice-only simulations and the forcing data sets that we need to drive them in the sort of situation we're in right now. There's kind of a lack of those data sets being available. So some context, sort of reanalysis forcing products have been used historically over many years to drive ocean and sea ice only models and land only models, the same models are used in the coupled models. And these simulations typically rely on long and accurate historical forcing data sets. They tend to be based on reanalysis products, a range of different reanalysis products like the NCEP NCAR reanalysis, the 20th century reconstruction, JRA 55 or ERA 5, or really any reanalysis product. But they always need to be bias corrected because the data coming straight out of those reanalysis products is not accurate enough, especially for things like precipitation, but for quite a few fields that are important for the ocean and the land, and so that can include solar radiation, long wave radiation, winds, and other things. And so the details of what the ocean groups and the land groups have done to bias correct them are slightly different, I think, and I don't even know all the details necessarily, but there's definitely a massaging effort that goes on, this fairly sizable effort to get these to be useful for land and ocean only simulations. An important feature is that they're long and self-consistent data sets, and in particular with no discontinuities. So we have in the past seen people try to merge different data sets together, and you can detect those discontinuities pretty clearly in the model output. I definitely know that's true on land. I suspect it's true on ocean as well. So for CMIP6, the OMIP, this is the Ocean Model and Comparison Project. So ocean-only simulations relied on a product that's called the JRA 55. So this is this JRA 55 reanalysis product, which was then adjusted to work well for the ocean models. And the LMIP used a product that was called GSWP3, which was based on the 20th century reanalysis product, and then bias corrected with a whole bunch of different things as a default, but then also had options to run with several different other products, one called CREW-NCEP, one called Princeton, one called Watch WFTEI. And I'm not going to go into the details of all these, but they're all different reanalysis products and different bias correction methods. And we did that in LMIP to sort of be able to explore the role of forcing uncertainty in land-only transient simulations. So I think I don't really need to go over this data set, over this slide, except for to say that, these different communities have been doing these kind of experiments for a long time. These are some old papers showing, they're called, on the ocean side, called the CORE reference experiments, coordinated ocean ice reference experiments. In the land, we've been doing it in support of the global carbon budget, for well over a decade now. So these multi-decadal ocean and land-only simulations are useful for a lot of reasons. Evaluation, understanding, improvement of components of the Earth system models. So, evaluating these models uncoupled helps us understand what happens, how the models evolve differently, or the processes evolve differently when you couple them. They're useful for investigation of mechanisms for seasonal, inter-annual, decadal variability. They can be used to contribute to, especially for the ocean attribution of ocean climate events, their evaluation of robustness and mechanisms across models, and a good way to bridge observations and modeling, because you're forcing the ocean and land models with actual or closer to observations rather than the coupled model where the models can diverge quite a bit from observations, and so it's harder to use ocean and land observations to validate these models. And importantly, and kind of a side effect, but a relatively important one, is that they provide initial conditions for ocean, sea ice, and land components of coupled Earth system prediction simulations. So that's could be like the CMIP or any other kind of predictions that people are doing more increasingly with these models. So it's an important mechanism to get initial conditions, or one strategy to get initial conditions for these models. And I just want to make one slide here on forcing uncertainty, or two slides on forcing uncertainty. There's many ways to do bias correction. There's these different reanalysis products. And within LMIP and CMIP6, we ask each group to run with different forcing data sets. And here shows different lines. So the upper ones here shows that CLM run with, that's a community land model, run with the Princeton data set, the CRU-JRA data set, and GSWP3. Are showing pretty different time series for the carbon accumulation key quantity in the land. And you see some models don't show as big a divergence as CLM does, and some models do. And so it's kind of interesting feedback that's going on with the forcing data set and the model configuration. And the second slide here on forcing uncertainty is that we ran looking at ILAM, the land model benchmarking package, we assessed each CLM5, the community land model version 5, with 3 different forcing data sets. And one thing that we found was interesting is that the data set that tends to agree best with observations, the forcing data set, as shown in green here, that's sort of a better match, also tends to produce a better model output. And so it's sort of unknown exactly, well, it sort of makes sense that would be true, but why that's happening is a little bit unexplored. Okay, so I just want to kind of finish here with what we're get into what we're planning for CMIP7. For LMIP, the situation is that none of the forcing data sets that were used in CMIP6 are being updated to present day, and so that's kind of a limiting factor. However, the Global Carbon Project has been producing a data set called CRU-JRA that is available through at least the end of 2023. Though CRU-JRA has some significant limitations, including the fact that it's 6 hourly, which is really not enough temporal resolution to properly resolve the general cycle. And so there's pretty known limitations there. And it doesn't have data for Antarctica, which makes it problematic for initializing coupled model simulations. And further, it can't be extended any further because JRA 55 reanalysis is being discontinued. On the OMIP side, the JRA 55 reanalysis has been discontinued. I just mentioned that, but it will be used as it goes through 2023 for at least the initial phase of OMIP and CMIP7. In both cases, though, this inability to extend to present day is going to impact our efforts to run near real-time decadal, multi-year, or S2S prediction experiments. So this is where it comes into fortunate that we recently were able to gain funding to support the production of the next generation data sets to force ocean sea ice coupled models, and we're going to try to extend out to the land based on ERA5. This is an activity that that's been supported by DOE and NOAA. I'll say in the next slide. So the advantage of using ERA5 as the basis going forward is it's obviously a trusted reanalysis product. Its spatial and temporal resolutions are higher than what we've been using previously, getting into the point where it's approaching the eddying range, I guess, for ocean models, quarter degree, and it's also hourly resolution, which is quite important for land. The bias correction data sets will need to be available and updated real time. ERA5 goes back pretty far to 1940. Ideally for land modeling, we'd like to go back further than that, but we can live with 1940 as the starting date. There's buy-in and support and collaboration from the ECMWF to produce the reanalysis product in the long term, or have a new product available if ERA5 goes away. There's an initial commitment for continued production of these reanalysis data sets, and there's no redistribution issues. As I mentioned, one limitation is that it doesn't go back to 1900 for the land, but I think we've proven that we can live with that limitation. So this effort started quite recently, funding from the U.S. Department of Energy and NOAA. It's a collaboration between NSF NCAR, NOAA, GFDL, and DOE LANL, along with CLIVAR, OMDP, and the International Ocean Modeling Community. Forcing over land is not explicitly part of the proposal, but the NCAR team is going to try to leverage this opportunity and pull it in and work on the specific bias corrections needed. So the result will be a data set, complete data set for forcing ocean ice and hopefully land simulations for 1940 to the present day for broad community use. Open access scripts and tools extendable for use in creation of future data sets. For example, if they transition to ERA 6 and a manuscript describing that. And there are some discussions about producing a forcing data set that can be used for projection periods using output from CMIP6 or CMIP7 simulations. So this is my last slide. The path forward is that we hope the CFORCE data set provides a solid baseline now, kind of resolving a hole we had in these two communities with the forcing data set for the ocean ice research community for sure. We're hoping that we can extend it to be usable for the land research community. Otherwise, the land research community is a bit out of luck right now. Except for we have this crude JRA data set, which can't be extended. We're putting a lot of emphasis on extendability so they can be updated. Nonetheless, ongoing extensions are going to require resources, which ideally would be part of any centralized CMIP forcing data set support. I don't know if you guys have talked about that here, but I know in previous meetings, there has been discussion about trying to find longer term support to support these groups that are putting together data sets. I'm not sure what the cost would be, but potentially in the range of 1 to 2 months of effort per year, to update these data sets on an annual basis. More if you want to make those better. Scientifically, one thing that we're not treating here, but we should, is accounting for observational uncertainty. As I showed, there is forcing uncertainty. We see that in the impacts in the land simulations, and it'll be highly beneficial. And there are efforts around the world to generate ensembles of historical forcing data sets that span this uncertainty that are not currently covered by CFORCE. So that is it. Stop there. Thanks.
Thank you, David. Questions for our last speaker? Yes, please.
Thank you, David. Very, very nice to hear about the fact that ERA 5 has been used, and that you already have planned for the use of ERA 6, which will contain coupling with the ocean to some extent. So that's very, very interesting. Something we are now starting to do is to look at ERA 7 and what will need to happen for ERA 7. So having feedbacks like those you provided in the presentation is very useful on what are the desiderata from your community in the reanalysis product. Also because since June this year, ECNWF has become the lead center for the assessment of global climate reanalysis. So in a sense, we have a way of interacting also with the other reanalysis center to potentially spread further your requirement in terms of new products. So that would be very useful. So in a sense, one question for me is, what would you like to see in the future reanalysis that is not there? I mean, some of the points you mentioned already, but we are approaching Christmas, so on your letter for Santa. And the second one was about the bias adjustment, because you said that a lot of the data set that you've used based on reanalysis requires some sort of bias adjustment. And I was wondering what sort of observation you use for the bias adjustment, and whether you think this can also or should also be coordinated internationally. So having a common methodology for bias adjusting, like a bit like the watch forcing data you were mentioning, that there is a WFD E5 now, and we are working on the next iteration. But whether an effort in the direction of common bias adjustment should be considered. Thank you.
Yeah. To answer the first question, I don't know if I have a wish list. I think people are always asking for more resolution. So as you go forward at any resolution, you increase mostly in terms of the spatial resolution, but temporal resolution as well. On the land, there's a little bit of a need to separate soil radiation between direct and diffuse, which typically we haven't been providing in these data sets. I don't know if it's a product that's available within the ERA 5. I've never actually looked. It's a good chance it is, and that might be helpful for land, especially for land. There may be other things I'd have to, I'd want to get a group of people together to talk about it. In terms of the bias correction, yeah, I mean, I think all these different groups who put together these data sets have maybe taken on slightly different methods to do the bias correction, and probably different data sets. I know, you know, they've used, like, a lot of them need long-term data sets, right? So going back, so CRU, because it's a long record for temperature and precipitation, has been a data set that's been used. And I know when we put together the initial versions of the GSWP3 data set, which was relying on CRU to do the correction, the preset backway in the, you know, the 1900s, but had some pretty big problems that we had to resolve, including no snowfall over much of the Arctic over many years, which was really problematic for the permafrost climate carbon feedback problem. But what I guess my biggest wish list would be is that actually ERA or ESMWF took on this project and actually took it over after we built this maybe C-Force, and took it on as like an operational thing that they produced, rather than having it being, you know, being housed at a place like NCAR. I think it would make more sense that it was all embedded together, and if we had scripts and whatever that did that bias correction in a certain way, you know, we as a community could keep updating those. But it seems more appropriate to me that it's being managed by ECMWF. But that might be too big of a wish.
Ben?
Hey, Dave. Yeah, nice talk. So the effects of the forcing data sets on the carbon uptake, the historical carbon uptake, was like pretty striking. And it was one, and on your last slide, you sort of talked about the need, or like how it would be desirable to have ultimately ensembles of, you know, plausible alternative trajectories. Like, is there, to what degree is there still information from that coordinated experiment you did on working out what the mechanisms were for the different rates of carbon uptakes as driven by the data sets? And could that then inform potentially what axes of forcing uncertainty could be developed if somebody had the time to do that ultimately?
We haven't done a really deep exploration of this, but my hypothesis, which is sort of borne out in the simple analysis we've done, is actually it relates a lot to what you get at spin-up. So the carbon stocks you generate, especially for vegetation carbon stocks at spin-up, will really affect your land use change flux. So if your model produces, you know, 200 petagrams more carbon on land, and you're cutting down those forests, and that's going to lead to a different trend. And so in some ways, it's not super interesting. But again, you know, that's sort of the truth of it. So that's, I think, what's happening with CLM, at least, is that we do see pretty distinct differences when you run with these different forcing data sets, that sort of equilibrium carbon state in 1850, and then that sort of just persists throughout the simulation.
Paul?
But I think there's probably more to be mined there. I know the hydrologists that we have here at NCAR kind of routinely run with at least, you know, precipitation uncertainty ensembles, and we've just never tried to do that with CLM. But I expect we'd start uncovering other things if we did that.
Paul?
Thanks for that, Dave. It's good to see that there's an IMIP data set that's imminent, which is excellent, because I know the JRA data set was something that was an excellent and pretty comprehensive product that Hiroyuki was producing. The question I actually was going to ask is, there was a number of subsequent, well, kind of ancillary data sets that he produced, like salinity restoring, freshwater forcing, all of that kind of stuff. Is it something that ERA 5 can also provide in addition to what, you know, JRA 55 actually provided? Do we have any holes?
I'm not sure I know enough to answer that question, being a terrestrial scientist. I could ask Gokon.
Well, Carlo's just actually asked a question across the table here, so I'll repeat myself. And asking the question of him, sorry, not to you, Dave. So the question was, the JRA 55 reanalysis product was what was anchoring the IMIP, original IMIP data product. There's now a toggle from the JRA product to ERA 5. And so one of the things that, in addition to winds and a whole bunch of other fields that were generated from the output from JRA 55, there was some things like salinity restoring and a bunch of other fields as well. With ERA 5, is there coupled consistency? Like, are there ocean fields, for example, that we'd actually be able to leverage from what SMWF actually has that would then provide consistent, things like salinity restoring data sets, etc.
Yeah, I look also at Anka over there and for confirmation of what I'm about to say. At the moment, the two are consistent, so the ocean reanalysis and the ERA 5, but they are somehow independent at the same time. So in ERA 6, there would be a closer coupling between the two. It's still a one-way coupling to some extent, but the trajectory within the assimilation window will be coupled, but then there is a sort of one way and so. Yeah, I wouldn't call it two ways, but still more consistent with one another than they've ever been before. For ERA 5, the connection is less direct.
We can find out more by asking our colleagues in the next day or so, if you really want to know.
Okay, there is also a question from John Dunn. Would you like to speak out?
Sure. So I was wondering, Dave, if there was any further engagement from CNRM on the land side. They seemed very eager back in January to embrace the ERA 5 solution. We're looking for funding, I think, as well towards that. Are you in collaboration with them at all, or is this independent?
No, this is independent, and no, I have not heard from them or tried to contact them. I either forgot or didn't know that they were interested in that. Yeah, this was, as you maybe know, John, this came sort of fortuitously out of the U.S. Climate Modeling Summit when we raised this as an issue, and it sort of grew out of that, and out of conversations from there. And the focus from the proposal is really focusing on the ocean, and the program managers didn't want to extend to land, so we're going to see if we can manage to extend to land here in-house with in-house resources. But if CNRM wants to help, I don't know, it's a little hard, that international collaboration, but I can check in with them.
Okay. Yeah, I think that with the 1 hour time step, the land should be a lot easier than the previous ones, but they'll still need the corrections, bias correction.
Yeah. Some of the bias corrections will overlap and some will be different. I think the land is more concerned about solar, for example, than the ocean is. 4-to-1 for the land and not quite as important for the ocean. So we haven't sat down and figured out what things we do differently between the land and the ocean. That's something we're planning to do as the project gets going.
Okay, thank you. Are there any more questions for David or comments? Okay, then thank you, David, for this presentation. There is maybe one more general question to all of you. Are we missing anything? Any data set, any forcing that you think would be really useful and we should produce? Piers?
I just wondered, what were we doing for aviation contrails?
Good question.
It's probably tiny, but it's there. And the other thing that isn't insignificant is actually anthropogenic energy. Energy from heating, yeah. Yeah, well, yeah. Sorry, I think they're of the order, each of them are kind of hundreds of a watt per meter squared, but each of them is going to be significant in particular locations.
Yeah, thanks for that contribution. Oh, okay. More comments? Yes, please.
Yeah, not strictly a forcing that we're missing, but one of the things that came up there was that sometimes the underlying data sets disappear. And how do we want to think about that as a community?
Yeah, good point. Yeah, traceability, data availability, and keeping it alive. Yeah. More comments? Yeah, please, Piers.
Yeah, I mean, just for context, when we were putting the IPCC chapter together, I was very conscious that the combined effect of land use and land use changes were not really on the IPCC ready to forcing bar chart. I mean, we just have the change of the surface albedo. And I'm just concerned that we have changed in evapotranspiration and irrigation, of course, have been talked about, but we have changed in roughness and things as well. And it would be really good to see all those elements brought together, perhaps in some way.
Ben?
Follow up to Piers' point before about anthropogenic energy use. I mean, could we consider this as being one aspect of the wider issue of parameters of urban spaces for those models which have urban models or have urban components? One could provide such urban models with time varying SSP dependent parameters of there's lots of aspects of urban evolution which could vary by scenario, right?
Maybe would tie in with land use. Luis?
Yes, we have the urban data in the land use data set by scenario, and they were all provided by one model from what I remember. But I think it's up to at the stage up to the system models how they take that urban data and whether they're parameterizing heat islands or other effects. We're just providing the area at this stage.
Okay. Anything else you would like to add to our list to do? No? Then I would hand over back to the organizers.
Okay, well, thank you everyone for all the discussion and participation today. It's been quite an intensive day. So now we have got a bit of an icebreaker downstairs in the weather room, I believe, where Carlo has kindly put on some food and drink. Okay, so thank you everyone online, and we'll be back again tomorrow at 9 o'clock sharp. Great, thanks very much.